Hello everyone, and thank you for joining us for today's Surface Measurement Systems live webinar. The title of today's session is The Effect of Surface Properties on Granulation Performance. We are very lucky to have with us here today to discuss this topic Dr. Daniel J. Burnett, our Vice President for Surface Measurement Systems North America. His team works on research studies and scientific applications for many prominent companies, and he received his bachelor's degree in professional chemistry from the Eastern Michigan University in 1997 and his PhD in chemical engineering from the University of Michigan in 2001. Dr. Burnett has authored and co-authored over 25 peer-reviewed journals and articles in peer-reviewed journals, and presented at numerous national and international conferences, and really is an expert on the subject of sorption science. Just before we get on with the presentation today, I just wanted to share a few housekeeping rules to make sure everyone enjoys and benefits from the webinar as much as possible. To avoid any background noise, unnecessary feedback, or anything of that sort, we do ask that everyone keeps their microphone muted for the duration of the presentation. As you may be aware, there is a live Q&A at the end of the presentation for which Daniel J. Burnett will be happy to answer any queries that arise on this topic, either from your own work or from the presentation itself. And you can submit these questions in one of two ways. There is a questions panel where you can submit your question in writing, and then I will pose that question to Dr. Burnett for him to answer. Alternatively, if you have maybe a complex question or a question where you may need to have a follow-up, you can raise your hand and then I will prompt you over the microphone to unmute yourself and you can ask Dr. Burnett your question directly. So once again, you can submit your questions in writing in the questions panel or raise your hand and I will let you know when you can unmute to ask your question. So without further ado, I will hand over to Dr. Burnett to begin today's presentation.
Thanks, John, for the introduction and for the housekeeping items for everybody. So hopefully we can all see my screen. John, just stop me if that's not the case, but I will move on. And everyone's time is precious, so we'll get right into it. So just a quick little outline of the presentation today. Very briefly introduce granulation. I will not profess that I am an expert in granulation in any way, shape, or form, but I will be talking about how surface properties, in particular surface energy, can be used to help optimize or study or problem solve when there are wet granulation or granulation issues when you're working with dry materials. So the talk will be focused on a series of case studies, some of them from our research, some that I have pulled from the literature, just to give a broader depth of perspective on how surface energy can be related to this important industrial operation. So in particular to the manufacture of solid state pharmaceuticals, there are several unit operations that are typically done in a classic dry formulation, let's say a tablet or whatever it may be. One of those unit operations very often is a granulation step. So this is not unique to pharmaceutical applications, but certainly agrochemicals, catalysts, foods, and other things very often have either a wet or a dry granulation step as part of the formulation and development and manufacturing process. So in general, granulation typically involves the co-agglomeration in pharmaceutical with some small crystals or API with some sort of excipient or a liquid binder with or without using a liquid binder. It's typically done to improve powder flow, compaction, uniformity. And what we'll focus on today is clearly granulation behavior is subject to a wide range of forces and properties. Surface energy can be one of them. Certainly, it is not the only important property. Many things that I will consider maybe a bulk property like density or morphology or dissolution behavior certainly can play a bigger role in certain instances. But we'll focus on the cases where surface energy or wetting characteristics could be important to the granulation behavior. So in general, the surface energy of the solid particles will determine the ability of the binder solution to spread across the surface of the particles. Therefore, selection of the correct binder and or wetting agent in granulation processes can be critical to the ultimate performance and stability of the final granules. The solid binder interactions can also influence the strength of adhesion and the strength of the granule, and very much related to the ultimate mechanical properties of the final agglomerates. As I mentioned at the beginning of this presentation, we'll talk about some liquid-based measurements to measure surface energy. Those are typically contact angle measurements. There are a few different ways to do this in the literature, but essentially it's measuring the contact angle of a liquid as it is interacting with a dry solid material. I'll also be talking about inverse gas chromatography as a way to measure the surface energies of dry materials. This is a chromatographic or gas phase technique. It can be applied to a wide range of surface morphologies, measurement conditions. We can readily control temperature and relative humidity. We don't have to make powder compacts or do anything special. We can measure the granules or the raw ingredients as is, and we can study a range of surface sites to look at energetic heterogeneity, whereas contact angle typically gives you an average surface energy of the entire surface that's accessible. And for those of you not familiar with the inverse GC, it is a chromatographic technique where we invert the roles of the stationary and mobile phase. I won't get into the details of that. Just part of our webinar series. We've done quite a few presentations. If you have some detailed or specific questions on inverse gas chromatography as a technique, we'd be happy to answer those. But essentially, we pack a column with the material of interest. We elute or introduce a single vapor or gas at a time, measure the retention time. This retention time is related to the properties of the solid. So it's not a technique that surface measurement systems invented, but it is something that we've been heavily involved with for the last 20+ years. And if we look at a histogram of references in Google Scholar to inverse gas chromatography over the last 40 years or so, we can see that it has grown in significance, in particularly since 1999, we came out with our first commercial inverse gas chromatography system, second generation around 2010, but you can see it continues to have a steady increase in importance in the literature. This is just a schematic. As I mentioned previously, you typically would have a carrier gas that pushes through a solvent through a column. We measure the retention time with a certain detector, in particular a flame ionization detector. The sample is typically packed into a straight column, needing between 10 and 900 milligrams of material typically to do the analysis. So without much further ado, I don't want to talk too much about the different techniques. I wanted to get directly into surface energy and how that can be used in some granulation case studies. Surface energy is analogous to surface tension of a liquid. So when we talk about some liquid-based binder systems, you'll see in the next couple slides, we do have some surface tension data of the binder solutions and or solvents used, and that is analogous to a surface energy of a solid. It is directly related to the thermodynamic work of adhesion, and it's very often divided into a dispersive or non-polar contribution or an acid-base or polar contribution. So depending on where you look in the literature, But essentially, we have a non-polar contribution and a polar contribution that will give you the total surface energy. And the surface energy of a solid will directly affect the wettability when you put a liquid on top. This could be a binder solution, it could be a pure liquid, but as we increase the surface energy of the solid, we'll increase the wettability of the liquid, assuming that they're compatible. If we think about powder flow or cohesion or agglomeration, if everything else is remaining the same and we increase the surface energy of the particles, we'll increase the interparticle forces and we'll increase the cohesive nature of the powder. We're not going to talk about milling in this particular study, but milling is another common unit operation in dry powder processing and in particular API development. But when you mill a material to either make it smaller or some other reason, not only do you make the surface smaller, but you often make it more energetic because you introduce defect sites or amorphous sites or buried interfaces that have higher surface energies. When you talk about formulation between two surfaces, if I increase the surface energy, let's say of these larger particles in red, and if I increase the surface energy of that with everything else remaining the same, I can overcome the cohesive forces of the smaller particles and I can increase adhesion. So when we're talking about interaction of a solid with another particle or a solid with another liquid or solid with some other surface, one of the main components of that interaction is the work of adhesion or the work of cohesion, which is directly measured by the surface energy. So if we look at adhesion, that's when we're looking at two dissimilar surfaces. So this could be the surface energy of another solid, or the surface tension of a liquid, or the surface energy of a surface. And we could determine the work of adhesion, which is the thermodynamic likelihood that two surfaces will stick or interact with each other. And we can compare the work of cohesion when we're looking at similar surfaces. So we're looking at an individual particle and how that might stick to particles of itself. And this could lead to segregation or agglomeration. And I do have a very quick study at the end of this talk looking at that type of behavior. So one common question that is often raised with surface energy is it a function of particle size? And from a particle size standpoint only, the surface energy is independent of particle size. So this is an energy density that it's a millijoules per, sorry, this is a wrong label here. So millijoules per meter squared is the surface energy. And so that means it's an energy density. So in this particular study, we took lactose crystals, crystalline alpha lactose monohydrate, just sieved them to different particle size fractions, and then measured the surface energy. And you can see that particle size or surface area by itself does not affect the surface energy of a powder. As I mentioned, it's not the focus of this presentation, but milling, when you grind or mill or put some high energy process to make a large particle into a small particle, you can often get surface energy differences. That is not due to just the surface area or particle size. It's due that we've actually changed the surface chemistry of the material by milling, grinding, blasting, doing some other treatment to it. So if you measure a change in surface energy after any unit operation, it is not due to surface area or particle size alone. There's an actually chemistry that's changed on the surface. So we're going to quickly move into some case studies. We'll look at some contact angle work that was done in the literature, and then we'll go on to some IGC case studies as well. So this is not an exhaustive search, and I'm sure there's many more studies, but I just wanted to show that there are several different studies that have looked at the influence of surface energy and how it might affect agglomeration or granulation behavior of primary particles. One of those was published several years ago in the Journal of Colloids and Surfaces. Here we're looking at basically two different solvents, water or a 20% by volume ethanol in water. So this is kind of the binding liquid with the same compound. So the compound is remaining the same. All that is changing is the binding liquid. So they wanted to use surface energy values to determine spreading coefficients, which is the likelihood of the binding solution to spread over the compound, and see if that could be used to predict granule properties. And this equation here is the spreading coefficient. The less negative, or the more negative the value is, the less likely it is for a binder or a powder or some other thing to spread over the surface of another. So this is the likelihood of compound or material 1 to spread over material 2. So here was the surface tension of the liquids. These are just from the literature. And then the surface energy of the solid here. And if we know the surface energy and or surface tensions, we can calculate the spreading pressure. So this is the dispersive or the specific. This is also what I called gamma AB. It happened to be called gamma SP for specific in this particular paper. So I use the same nomenclature. If we know all these components, then we can calculate the spreading coefficient. So if this is from a predicted value of the individual components, we would suggest that the 20% ethanol in water solution would make a better binding or spreading agent onto the drug. And the granules were made under similar conditions, and then both looked at the density of the API by itself. And then when water and or 20% ethanol in water was used as a binder, and we can see from the porosity and the friability that the 20% ethanol solution had a higher wettability, led to a lower porosity and stronger granules, as noted by the lower friability. So the surface energy values predicted that this would be a better binder solution, and the actual granules mechanical and or bulk behavior proved that to be true. So moving on to another case study. This was done by Hercules. It's a little bit old, but this was done by looking at the different binders and different APIs. And again, looking at how the surface energy and or surface tension, this was happened to be using Washburn approach to look at the API surface energy. And you can see here, this is the surface tension of the different binder solutions. So this shows that HPC had the strongest wetting behavior with the lowest contact angle. High contact angles indicate poor wetting or poor drug binder interaction. So this was the for the different solutions on ibuprofen. So this is where a droplet of a liquid was put onto ibuprofen surface and then measured these contact angles and surface tensions. And we can see here from the actual tablet behaviors under similar weight percentage of binders, we can see that HPC showed a stronger tablet performance. Again, the wetting behavior predicted ultimate tablet performance for these different granules. Same approach was done with a different API. This is naproxen. Again, the surface tensions and the contact angles we can see here. And we can again see that this was showing that HPC had the lowest contact angle, the better wetting behavior. And we can see that is the case here as well. So again, wetting and surface energy data correlate to tablet strength. So we went through some liquid-based contact angle studies. They certainly have a place and a value, but clearly, when you're looking at very subtle or sophisticated differences in surface energetics of dry materials, IGC has proven over many years to be a bit more sensitive in looking at subtle differences in surface energetics of dry powders. So I'm going to talk about a few case studies related to granulation and surface energy measured by inverse gas chromatography. So this particular study, we're looking at a model glass bead. So this was used as a model material because we could use it and control particle size, so we could keep particle size, keep density, keep surface area, keep everything exactly the same, and only control the surface chemistry. So we wanted to rule out any other bulk effects by using this as a model material. So we looked at both hydrophilic and hydrophobic glass beads. So these basically have a surface treatment that make them hydrophilic or hydrophobic, and different particle sizes. And the binder that was chosen was an HPC, hydroxypropylcellulose, as the binding agent. The granule properties were done by fluidized bed granulation, and we used some particle size distribution measurements and imaging to assess the granule properties. So again, the goal was to use IGC to measure surface energetics of the individual components and see how that correlated to ultimate granulation behavior. So here we can see it's a little bit busy here, but this is the surface energy at infinite dilution of the individual components. Here's the HPC. For comparison, this was PVP, and then these are the hydrophilic and hydrophobic at two different particle sizes. So we can see here that when they're at the same particle size, we see no difference here and here. So particle size has no effect on the results whatsoever. And in this study, we also used several polar probe molecules to look at the Gibbs free energy, or the delta G. This is in kilojoules per mole. And this kind of gives us a fingerprint, let's say, of the relative surface chemistry of the individual surfaces. So this is the primary particle, and this is one of the one hydrophilic, one hydrophobic, and this is the binder agent. So this is what the individual particles and starting materials look like. And then we actually made some granules with the HPC binding agent. And here you can see these are some pictures of the quote unquote hydrophilic beads. It's a little bit hard to see, but you can see kind of this complete coating and wetting of the binding agent. And you can see a 0 degree. So this is basically here. And most of the binding agent is spread out over the glass beads, and only a small amount is left to make some liquid bridges and actually bind different particles. Now from the hydrophobic beads, we can see quite a bit of difference. So this is again at the same binding solution ratios. There's quite a bit because the binding solution doesn't completely wet the beads. We can see that there's a significant amount left to make liquid bridges and make agglomerates. And here is some macroscopic pictures of the granules after they were made. Here you can see the hydrophilic beads here. You can see mostly small granules. These are the hydrophobic. You can see there's quite a large distribution in granule size and granule shape. Some rather large granules, some small ones. And here we can see the particle size distribution. So this in blue is the hydrophobic particles, and you can see, although it does have some at lower particles, it certainly does, but we see more at the high end of these very large granules that are not present in the hydrophilic beads here. So we can see that the surface chemistry, again, the exact same size, shape, density, surface area of glass beads. All we're changing is the surface chemistry of that. It makes a dramatic difference on the granulation behavior. And if we look at the final granules, so we looked previously at these are the raw ingredients, kind of looking at a fingerprint of the surface chemistry with these different polar probes. Now we're looking at the final granules, and we can see that the fingerprint, let's say, of the granules with the hydrophilic look very similar to just pure HPC, because for the hydrophilic granules, the HPC completely covers the surface or wets the surface to a higher degree than the hydrophobic granules. So the hydrophobic is some mix between HPC and the glass beads, whereas these two surfaces look very similar, most likely because the HPC is completely coating the hydrophilic granules and not the hydrophobic granules. So just to summarize this case study, the binder appears to spread on the hydrophilic glass beads, which results in coating. The hydrophobic shows kind of islands of binder and solid bridges can be formed. And this allows the hydrophobic beads to show larger granules as solid bridges, although the size distribution is wide. And I'm not saying these are optimal granules that you'd want to use, but it's just showing how the surface chemistry can certainly change the granulation behavior. Okay, my second to last case study, I believe, is again looking at the change in surface properties and how that can affect granulation. Here, this particular study was looking at a single API, 2 different binder solutions, and looking at both IR spectra and the surface acidity and basicity as measured by IGC. This is not our work here, so I just wanted to make sure we give credit to the work that was done previously. So again, the ultimate goal was to look at surface characterization to study and predict granule behavior. So this is looking at the Ka and Kb, or the Kd, which is the base, and the Ka. This is a property that can be measured by IGC. I won't get into the details of that, but essentially it's a way to look at the relative surface acidity or surface basicity of any dry material. This is also what's called the Gutman acid-base numbers of it. So this Kd is sometimes also called Kb, but it's for a donor and acceptor. So we have the surface basicity and surface acidity measured by IGC. So we can look at you can see that the solid bars are the spray dried samples before and after granulation. And we can see that this is the ratio of the basic number or the donor number to the acceptor number. So this is before and this is after. So we can see that on all cases, this granulation step increases the surface basicity of the materials. So the greater change in surface chemistry was when there was a binding agent. This increase in electron donating properties was increased due to the change in surface groups, and the IR data was consistent with the change in surface carbonyl groups. So we can see that both IR and IGC experiments suggest that granules have heterogeneous surfaces and the drug polymer interactions are limited to the surface. So this is not a granulation per se, so we don't have a liquid in this case, but we're looking at the mixing of different powders and how they can maybe segregate, and this is all based on the surface energy and or the work of adhesion and work of cohesion and the spreading coefficient of the different materials. So the drug we're looking at in this case is acetaminophen with 3 different excipients. So we're just looking at a dry mixture of these materials, and we wanted to see if we could use IGC to measure the surface energetics of the individual components and compare to the physical mixing results, and to see if the spreading coefficient in the first case study, we looked at the spreading coefficient of a liquid onto a dry powder. Here we're looking at the spreading coefficient of a dry powder onto another powder, and to see if that correlated to any of the mixing performance or the actual performance of the quality of the blend. So we see here, so this is of the actual blends. So this is the mixing results. This is the acetaminophen with mannitol, acetaminophen with Prosolv, and acetaminophen with Avicel. And we can see here that this one predicts that this Avicel would be the best blend, was the best blend, had the least amount of segregation after the mixture was performed. Here we measured the surface energies. The solid is the dispersive, the shaded is the acid base portion of the surface energy. This was done at infinite dilution for these particular, this is again the individual ingredients. From the surface energy of the different excipients. We can measure the spreading pressure with the acetaminophen, and we can see that the spreading coefficient we can see here for mannitol, Prosolv, and Avicel, and we can see that the data here of the spreading coefficient agrees with the performance that we see here. And we can see here, again, low spreading coefficients was good. And we can see here that the mannitol had the highest spreading coefficient, which in this convention, I flipped the negative sign, so this would be the most negative. It depends which one you put, 1/2 or 2/1. But for this case, the predicted spreading values based on the individual components showed that Avicel would be predicted to make a more uniform blend, and we do see that in the mechanical behavior as well. So in summary, surface energies can elucidate various information about granulation studies. In this particular presentation, I've highlighted both contact angle and IGC experiments. If you want to look at direct binder interaction, that can only be done by contact angle. You can't do that by IGC. But IGC measurements allow for more precise surface energy determination and allow for heterogeneity profiles, which I didn't get into in this presentation, but in several of our other presentations, we can show that real world materials are energetically heterogeneous. And it's very important to study the entire surface chemistry or surface energy of a dry powder. So as I wrap up, I wanted to make sure I left ample time for any questions. I want to thank my SMS collaborators, both current and former, and certainly your time and attention. And as I pause for any questions, either directed from John, I will leave up our upcoming webinar/workshop series. You can go to our website and get access to these upcoming webinars in the next few months. So I will pause there and open up the floor to any questions that may have arisen during the presentation.
Thank you, Dan. That was a great presentation. And yes, for our audience, I'd like to remind you, you can submit your questions in two ways. You can submit them in writing in the questions panel, or if you would prefer to ask the question yourself over your microphone, please raise your hand, and I will let you know when you can unmute your microphone to ask the question.
I do have one question for you, John. Was this presentation recorded?
Yes, it was.
Okay, so I believe you can get access to the presentation after the fact. We'll make it available if you request it. So just wanted to let the audience know that if I was unclear or went through some things quickly and you want to take time to digest it, please, by all means, you can do that. And you can always contact us at science@surfacemeasurementsystems.com if you have follow-up questions that may come to you after this presentation. So John, go ahead if there's any questions from the field.
Thank you, Dan. So we have our first question here from a Ravi Raya, excuse me if I pronounce this incorrectly, Ravi Raya Parapu, and they ask, can you please give more details on the particle size of the AP and excipients and technique of mixing, the dry mixing?
I'll have to go back and look if we're talking about this one here. If I remember correctly, we were looking at the acetaminophen was larger in particle size, and these were smaller in particle size. I can go back and look at the case study, and we do have access to those. So this is one of our case studies that was published a while ago now, but we were mindful that we were trying to look at the ability for the excipient to coat the acetaminophen. So the acetaminophen was purposely smaller particle size than the excipients. But I don't know the exact numbers, but that's a good question.
Thank you. Our next question from FD Hadlitofis, and they first they thank you for some interesting case studies, and they ask, in wet granulation, it can be the case that the binder is added dry separate from the liquid. Is there any relevant literature in that field?
Directly, I'm sure there is. Off the top of my head, I would have to look for you, but I mean, it really doesn't. The concepts and the theories would apply no matter if it's in a dry phase or a liquid phase. The initial mixing or initial powder to powder wetting would be driven by surface energy. Clearly, there are other forces and other factors. You know, loading would play a role. Any mechanical pressure would play a role. Certainly, if there's a dissolution or a dissolving of one component into another, those would be driven by bulk processes, not by surface processes. But the initial and the adhesion or cohesion or interaction between any of the dry ingredients is driven by surface energetics. So I have to look to see if there are. But I do know that there have been some dry granulation studies. I can take a look to see what I can find out, or message me offline and I'll take a look for you.
Thank you. Gary Hollenbeck asks, can a mechanical process like extrusion overcome component surface energy differences?
That's a good question. I mean, in extrusion, it's probably more driven by the solubility of the different components and not necessarily the surface energy. So certainly there's been some solubility parameter and general solubility work in looking at, let's say, like a hot melt or some other extrusion process, because that's more liquid with liquid. Once it's heated, it may be more driven by solubility parameters rather than a surface energy. The initial mixing, if the dry ingredients are put in initially dry, then that could be driven by a surface process. But once it goes to a liquid phase, if I'm understanding the question properly, and I'm certainly not an expert in extrusion, but then usually surface properties are diminished and bulk properties become more important. So I would look at more like solubility and those type of things as maybe that's something that might be more important. Which solubility parameters can be measured by IGC, which is another area of talk. Those are more polymer properties rather than crystal and surface properties.
Thank you. And our next question is from Manoj Kumar Pathpi Reddy, and they ask, is there any way to correlate surface energy by DVS and IGC?
That's a very good question. Yes, in certain cases. So the advantage of the IGC is that you're typically under very low concentrations, and the interactions that you measure have fast equilibrium in the vapor phase because you're only doing a pulse of a particular vapor over that. So you typically do not have to worry about any bulk absorption where the liquid of interest or the probe molecule of interest actually interacts significantly with the bulk of the sample. In the DVS, you make a step change and you constantly feed that vapor or water or whatever the solvent may be to the material. And when we're measuring the mass change, we are measuring both a surface and a bulk interaction. So for a lot of organic APIs or excipients, particularly like PVP or HPC, you'll get a significant amount of bulk uptake in a DVS. The surface energy or spreading pressure measured by DVS assumes the isotherm has only surface interactions. So unfortunately, for a lot of like pharmaceutical ingredients or food ingredients or polymers or amorphous materials, DVS is not my first choice of technique to measure surface energies because the resulting isotherms are often bulk uptake and surface uptake. That's a long answer, but if you look at like minerals or inorganic rigid materials, you can very often get good correlation between the two techniques. So yes, you can, but DVS can be limited in how it can be applied to measure surface energetics because you have to have the right type of vapor interaction. It can only interact with the surface and cannot interact with the bulk. In the IGC, it's much easier to control that, and those are typically not a challenge to deconvolute surface from bulk in inverse GC because we work in a much lower concentration regime.
Brilliant, thank you. And our next question asks, what are the limitations in using surface energy data with regards to granulation behavior?
So the limitations are that it's only going to help solve problems when the issue is with a surface phenomena. So surface energy is a pure surface measurement. So if I'm working on a formulation or a granulation step and surface energy doesn't play a role, then IGC is not going to be the technique that's going to give you any additional information. As I mentioned, in some other, it could be a solubility parameter or a bulk property, or it could be density of the material was more important, or it could be, the dissolution is going to be more important, or the porosity more important. So it won't apply to every system. I mean, you can measure it, it'll give you a value, but it may not be the critical value that's going to improve or something that you can use to adjust a formulation. It has to be something where surface energy plays a dominant role in the interactions.
And Fortas Wissam asks, how can we increase the energy surface?
So there's lots of ways, by either surface modification, either by adding in or coating the material with a higher energy surface. Certainly milling and grinding, whether that's on purpose or by not, that often does increase the surface energy. If you get outside of things like in pharmaceutical, you get to where they do like plasma or ozone or some other activation process to make a surface more reactive or more or higher in surface energy. But I would say in organic powder processing, probably milling, whether it's so it's probably the mechanical processes that you can do if you wanted to increase. So typically smaller particles have higher surface energy, not just due to particle size. It's because by making them smaller, I've increased the surface energy of that. So the flip side, in passivating or making lower surface energy is a little bit easier. You can use some surface modifiers, or you could coat it with either a liquid and or another dry powder, where you can do like mechanofusion to lower the surface energy. Higher surface energy, you typically have to add energy to the system to increase the surface energy of the material.
And Fortas also follows up with, can the morphology increase the surface energy?
Certainly the morphology can change the surface energy, only if by changing the morphology, I'm exposing different surface groups that might not be there. So for instance, if I have like a needle-like shape thing like mannitol, and I mill that, I will cleave it along a different crystal plane, so I get shorter crystals. So therefore, the end groups become more significant into the surface energy. If I have a rough surface, I'll increase the surface energy because I'm exposing different surface sites that wouldn't normally be there. So also, if I've maybe compressed or done some other mechanical process to change the morphology of it, I will alter the surface properties of that material.
Brilliant, thank you, Dan. I think that's all the scientific questions we have from the audience. Just to answer Diamante Mache's question, yes, we will be making the recordings and the slides available after the session. So one of our team will be in touch with those in the next week or so. I'd like to take this opportunity to thank you once again, Dan, for being here today to give this presentation and answer our audience's questions. Do you have any more points you'd like to raise before we finish up for the day?
No, I just want to thank everybody for their time. And again, if you are interested in future webinars, there's a list here, and you can contact our science team directly, as I mentioned, through this email, or you can go to our website and you can contact us through there. And thanks again for your attention.
Yes, and thank you to our audience for being with us today, and thank you once again to Dr. Burnett. As Dan mentioned, we have several upcoming webinars scheduled, so you can check these on our website. And tickets have also just gone on sale for the Sorption Science Symposium 2021. This is the virtual event that we'll be hosting in September. covering the full gamut of absorption science topics, including materials characterization, IGC, and DVS techniques across a range of industrial applications. It's a great meeting place, and it'll have a really informative agenda featuring some of the world's leading experts in this area. And for those of you who attended our IGC symposium in February this year, you know, it's a great few days to really get up to date and reconnect with your colleagues and like-minded peers around the world. So if you want information on that or to purchase your tickets, you can just go to our website and you'll be able to find it quite easily. So thank you all once again for being with us here today, and wherever you are, I hope you have a wonderful remainder of your day. Thank you.